So what we'll do now is we'll use the master theorem, as you saw before, right? So this Rademacher non-commutative of kinship to go towards an inequality that will look a lot like a Bernstein inequality type thing, not for the tails, but for the expected value of the spectral norm. But as we saw, going from expected values of the spectral norm to tails is possible, right? And so I want to show instead the proof of these controls of the expected value, because right? I think you'll learn more from these proofs, and in fact, what is bounded in the proofs can be adapted very easily to get tails. And moreover, with these proofs, it's much easier to see where these logarithmic factors come from and where this potential of this optimality come from. Okay, so let's recall this master theorem, right? So master theorem is that takes it's for Rademacher series. So we take H1 through Hn d by d symmetric matrices. They're deterministic, they're fixed. Epsilon 1 through epsilon n are ID Rademacher random variables. They're independent Rademachers. They take +1 and -1 with probability halves, and they're all independent. And now the control is on the expected value of the spectral norm of this, and we even have the precise constant. Right, and so what we'll do today is we'll use this theorem to prove a series of theorems that become more and more general. And the proof of this will be shown in next lecture. Proof to be shown later. Okay, so we'll start with the theorem for positive semi-definite matrices. Okay, so let me tell you a little bit about what the strategy is going to be. And if we take H1 through H, now we want to get to inequality that controls sums of independent matrices, like X1 through Xn are random independent matrices, and one independent sum. What we're going to do is we're going to come up with a trick to be able to put an epsilon k in front, right? So if they were symmetric, as symmetric random variables, right? They're all symmetric matrices, but as symmetric random variables, meaning the random matrix X has the same distribution as minus X, then we could just put epsilon k, right? And we could have, right? So let me just write the strategy very, very quickly, right? So if we have these random matrices, right? If we had that xk was distributed as minus xk, right? If they were symmetric as symmetric random variables, then then writing the sum of the xk would be the same thing as writing the sum of epsilon k xk. And we could condition on the xk's and use the master inequality. Right? By conditioning in the xk's and using the master inequality, we arrive at needing to control something like the sum of the xk squares. But the xk squares are positive definite matrices. They're sort of always positive. And so by that point, we don't have to control cancellations, and this will make it a lot easier. And so we'll start, right? And so if we were to do this, we have to control something like this quantity. Right? But these matrices are positive semi-definite because they're the square of something. And so actually the place we're going to start in this series of theorems that we're going to prove is controlling sums of positive semi-definite matrices, exactly because of this fact, and then we're going to use that to do something of this type. Okay, so we'll start with positive semi-definite matrices for this region. Okay, so let's do that. Okay, so we'll start with positive semi-definite matrices. Okay. So let T1 and Tn be independent, random matrices, satisfying that Tk is positive semi-definite. Okay. So when I say this, I also mean also symmetric. Right? When I write this, I mean that the eigenvalues, like the eigenvalues of Tk, are all bigger or equal to 0, and that it's also symmetric, right? Meaning that Tk is equal to Tk transpose. Okay, so that's what I mean here by symmetric, right? There's this sort of unfortunate thing in notation that there's these two meanings for the word symmetric. There's the meaning that a matrix is equal to its transpose, right? It's the linear algebra symmetric. And there's the meaning that a random variable is distributed as equal minus the same random variable, right? So here I mean symmetric as a matrix, and sometimes I'll use the other symmetric. I'll try to make it clear from context. Okay. Now the theorem says the following. Okay, theorem. Okay, we can do theorem here. Theorem. Right, the sum of Tk going from k from 1 to n, spectral norm, expected value of this, is smaller or equal than, right? And now we have a big bound. Let me do exactly what we have here. Okay, so we have a big expression, but it's going to be exactly what we'll need to fit in the other one. Okay, square of this, and now we have a term that has the expected value of the TKs, right? Because the TKs don't have expected value 0, right? I mean, in particular, they can't because they're positive semi-definite, right? So we have a term that contains the expected values of the TKs, square root, plus square root of a dimensional term CD, which is basically the square of what's here. The double what's here, basically, or 4 times. Right? Okay, let me see if I can write everything here. Expected value, okay. Plus square root CD times, and now there's another term here. Expected value of the max. Square root, and the whole thing is squared. Okay, so this multiplies by this. Okay, so we have expected value of the spectral norm is smaller or equal than the square of a term, the square root of a term that involves that has the expected values of the TKs plus this dimensional term that I'll write down times this maximum, right? It's a bit like this maximum in the Bernstein inequality. And CD is equal to 4 plus 8 square root of log d. Okay. So now we'll go ahead and prove this. So, you know, a bit like a cooking show off camera, I organized the board a little bit better, and I put the theorems here. So now we're going to prove this PSC theorem, right? The one that was just right here. And what we'll need is the trick that we'll use will be symmetrization, right? The idea is to transform a random variable into a symmetric random variable, because at the end of the day, we want to use this theorem where we have random plus or minus 1 showing up. Okay, so I'm gonna isolate that in the lemma. Right, this is called symmetrization. Okay, so just to say it again, here symmetrization means the symmetric in the sense of the random variable x being distributed as minus x, not in the sense of the matrices being symmetric. Right? All the matrices we have so far are symmetric in the linear algebra sense. Okay, so what this theorem says is the following: T1, Tn random matrices, let's say symmetric, as in linear algebra symmetric, not like Tk, this is not needed. Right? The positive semi-definites here will not be needed. And the theorem states the following, that sum of Tk, the expected value of the spectral norm of the sum of the TKs is going to be bounded by a term that has the expected value. This is a very general statement, plus twice a term, and I'll write it, a symmetric term. Right, where these are Rademacher random variables. Okay, and so the point is that with a theorem like this, we can go from something where the random variables aren't symmetric, right? And we couldn't use things like this massive theorem to control an expected value and then controlling something that is now symmetric, right? This random variable is distributed the same thing as minus this random variable because there's a Rademacher, right? And these Rademachers are independent, and we just pay a price of 2. Okay, so this is the idea of symmetrization. So let me prove symmetrization. Okay, so we'll start to prove symmetrization by, right, so let's just write these things out. So we have the sum of the TKs. Right? Now, just by triangle inequality, this is the same thing as taking the spectral norm of expected value of the TKs and we'll start by centering our random variables, right? We won't make them symmetric quite yet, but at least we'll center them. So now this is, now we have this expected value term, and we have our centered random variable here. Okay, so let's write here. Let's write here so that I can erase this. Symmetrization. No PSD needed. So symmetrization says following expected value of, this is just, I've been collecting all the theorems here to be a bit easier. All right, there is, okay, I mean, the sum or the expected value, doesn't matter which one comes first. Okay, so far so good. Oh, there's a 2 missing. Let's see. Okay. So now, right? Here, let me resolve this part. Now I can do this. Okay, so now we have centered. Now this is centered. Right, so now we have centered random variables, we just have to make them now symmetric. And now there's a really neat trick. So the trick is to create random variables tk prime that are distributed as tk and independent. Right, so the trick will be to create such random variables and to notice the fact that now tk minus t prime k, this random variable is symmetric. Right? Why? Because, well, you have a random variable minus something else that's equally distributed, right? Distributed exactly the same thing. If I take minus this, it becomes this minus that, but they're at the same distribution exactly. Okay? So now the trick will be to introduce this random variable, t prime k, and exploit the fact that it's symmetric. And because we introduced another one is where exactly this 2 comes from. Okay? So let's see, right? In particular, what does it mean here to be symmetric? Right? One way to say this is that tk minus tk prime is now equally distributed as if I hit it with the random operator. Okay, so let's keep the proof. Let's keep going on the proof, and let's bound now this term. Okay, so now we have, right, so this term already, the random variables are already centered. You have the sum of tk minus expected value of tk. Okay, so far so good. All right, now let's introduce this other random variable. Okay, so this is now equal, right? I'm just going to add by 0. I'm just going to add t prime k and the expected value of t prime k. Okay, so now you have the expected value on the random variables t. Okay, and now I'm going to take the expected value on the random variables tk, t prime, right? Inside, this is going to be inside the spectral norm. Right? And now what do I have? I have the sum of tk minus expected value of tk, right, minus tk prime minus expected value of tk prime. Okay, so let's first check that this is true. Well, this is easy to check because we have the expected value with respect to the t prime here, right? This can go inside, and the expected value with respect to t prime of this is 0, right? So I'm just adding 0. Okay, so far so good. But now, right, it's also true that this expected value is the same as this expected value. So I can also cancel out these terms. Okay, so what do I get? I get that this is equal to expected value in t of expected value in t prime of the sum of tk minus tk prime. Okay, so far so good. They're showing up these tk minus tk primes. But now by Jensen, right, I can move the expected value on this side and only get bigger. So now this becomes the expected value on both t and t prime of the sum of tk minus tk prime. Okay, so we're almost there, right? Because now this is exactly the same. Okay, let's go a bit more over here. Right? But this is exactly the same if I put an epsilon k, because now this random variable is symmetric as a random variable. It's equally distributed to minus itself. So this we get expected value with respect to everything of spectral norms of the sum of epsilon k tk minus tk prime. Right, because this is equally distributed, because this is symmetric, so anything around the macro-random variable is nothing. Okay, but now I can use again triangle inequality. Right, I can just split the term in tk and the term in tk prime. So this is smaller or equal than expected value of sum epsilon k tk plus expected value of sum epsilon k tk prime. Right, but these things are exactly the same, so this is just equal to twice the expected value, the sum epsilon k tk. Right, and we get what we want. Okay, proof finished. Right, so the point is that we can make essentially we can make any random variable symmetric by centering and then paying a price of 2. Right, this is a really useful trick. Okay, so now using this symmetrization, we're going to prove our theorem about positive semireferent matrices. Okay, so let's erase this proof. And this sequences of proofs follows essentially almost line by, follows exactly the ideas in a note by a very nice note by Trop that is referenced in the lecture notes for the course. Okay, so now that we have symmetrization, we can go ahead and prove our theorem. We can prove our PSD theorem. So proof of the PSD theorem. Okay, so let's see. So we can start by symmetrization, right? We have that the sum of tk's are smaller or equal than, right? We have exactly now, right? We have a term that looks like this. Sum of the expected value of the tk's. Plus, now we get twice right? We get twice the sum of the expected value of epsilon k's tk. So we get twice. There's an expected value missing here. Okay. Okay, so now we're going to, of course, use our master theorem, right? Because now it's ripe for using the master theorem. So the master theorem gives us, right, that this is smaller or equal than, right? What we get over there, half of square root of CD, right? But we get a 2 here, so we just get square root of CD times this variance term, right? I mean, we're using the master theorem conditioned on the epsilon k's, conditioned on the tk, so we're just using it on the epsilon k's. So we still need expected value with respect to the tk's here, the sum of the tk squared. Okay, so let's write that. So we have that expected value of sum k's are smaller or equal than, we get the expectation term. Plus square root of CD of okay. But now, since the TKs are positive semi-definite, now what's going to be the strategy? Maybe I say, okay, so I'm missing a square root here. Okay, what's going to be the strategy? The strategy will be to make if this factor looked like this one, right, then we could send it over here again, and this would give the inequality that we want. So we want to make a factor like this show up. We want to make a factor like this show up here, right? But now because, right, since the TIs are positive semi-definite, the TKs are positive semi-definite, it's not hard to see that we have that, the spectral norm of the sum of the tk squared can be bounded by just the maximum spectral norm times the spectral norm of just the sum of the tks. Right? Squares here. Right? So if we have the sum of the squares, you can just bound it by taking the biggest one, the biggest term in spectral norm, and then the sum on the other side. Right? Because the positive semi-definite, basically there's no cancellation whatsoever. Right? If there weren't, there could be cancellations here. But since there's no cancellations, this holds. And so now we're basically there, right? Because now what we have, okay, let's write our expression. What we have is that the sum, the expected value, sum of the tk's is now smaller or equal than, there's an expected value term, plus, and now we have, right, we have square root of CD times the square root of this we can put the square root here, times the square root of this term. Right, so we have expected value for now outside. Okay. So now we just need, to move the expectations inside so that this term shows up here, right? But this is just Cauchy-Schwarz, right? We can think of this as the expected value, right? Is the product of these two things as some kind of inner product, right? It's small, it is an inner product. It's smaller or equal than just the product of the norms, which is exactly moving the expected value inside, because the expected value is the square of this, square root of that, right? So this is smaller or equal than the same thing plus square root of CD. And now we can move the expected values inside. Expected value of the max, tk square root, times square root outside of the expected value, of course. Right? Because it will be the integral of the square of this, and then because it's a norm, is a square root on top. Okay, and now we just finish using the quadratic equation, right? We just finish using the resultant formula for the quadratic equation, because now this term is showing up here as a square root. We can see what this bound gives in terms of this, and it gives exactly this, right? Just use the quadratic resultant equation. And so what we have is, right, so for this finish, if you just use take this to be a variable x, the square root of this, you have x squared smaller or equal than something involving x, just work out the quadratic equation and you get exactly that. Okay, so this one now is proven. So we proved this one, and we're going to now use that to go into something a bit more general. Okay, and in particular, we're going to drop the PST constraint, right? Because now we can control basically squares of matrices. It's going to be easy to control just general ones because we're going to use symmetrization, and we can, even if these are random, we can control them because they correspond to positive symmetric matrices. Okay, so now we're gonna write a theorem for just symmetric matrices. So theorem y1 to yn It's going to be random, independent, random matrices. Let's say D by D, right? And symmetric. Symmetric in the sense that yk is equal to yk transpose. And we're going to come up with an inequality for, and this will look a lot like a Bernstein inequality type thing. In particular, what we'll say is the following. The expected value of the sum of the yks is going to be smaller or equal than square root, right? There's these dimensional factors, CD sigma plus CD L, where sigma is our variance parameter, right? So sigma squared is just expected value, of course. And L is just going to be the maximum, the expected value of the maximum. Okay, of this square. Okay, so it's a bit like Bernstein, right? Where this is being controlled by a variance parameter and the maximum all of them, right? In Bernstein, the matrices all were bounded by some R, right? This plays the role of this L. And now from this one could obtain then a tail bound, for example. Now that we have all the ingredients, proving this will actually be quite easy. So, because basically we have all the ingredients now, right? And so proving this is almost trivial now, right? So let's go ahead and do it. Well, we're going to start by using symmetrization, right? So, okay, of course for this theorem they need to be centered. Right, otherwise there would have to be another term, of course, right? So they're centered. And now proving this theorem will be almost trivial, right? So by symmetrization, remember that symmetrization need not the matrices to be positive semi-definite, right? PSD is needed. So we can use symmetrization here. What we get expected value of sum K1 through n of yk is smaller or equal than. Okay, so this term is 0 because the expected value of these of these matrices is 0, and we get twice the expected value of epsilon k's yk's. Right, so by paying a price of 2, we made the variable symmetric. Now we can use the master theorem. Right, so this is symmetrization, this is the master theorem. Right, so for the master theorem, we take 2, we take expectation, but now only, of course, on y's, right? And the expectation on epsilons, we're going to use the master theorem form. What does it give? It gives that this is smaller or equal than a half, which cancels the 2. Right, square root of CE, which you can put outside. Okay, let me be a bit more, write a bit better. Expected value, of course, just on y, right? So we're going to do this, replace with that. The half cancels with the 2, we get square root of CD. And now we get square root of this. Sum expected value of the yk's square root. Right, but now by Jensen, we can move the square root outside, right? It's the same thing as when we move the square inside the expectation, right? Since the square root is concave, so this is now Jensen. Right, Jensen gives the square root of CD. Right, now expected value in y, of course, of, okay, this is of course not here, sorry. Right, we're using this inequality, we just get it's a sum rather than expected value, like that. Right, so we get sum the yk squared, all of this square root. Okay, so far so good. Now this is a positive semi-definite matrix, so we can use the positive semi-definite matrix theorem. Right, so here we can use PSD theorem, right, because the yk square, because they're squares, they are positive semi-definite. So now what do we get? We get square root of CD times the square root of this, but this is a square to start with, right? So we can, the square root cancels with the square, and we just get sum of the TKs, right? Oh, there's an expected value missing here, of course. So, and the theorem here. Right, so we get the sum, expected value of the yk squared, right, square root. Right, this is the sigma term, it's exactly sigma, plus square root of CD times, right, and now there's going to be another factor here, and the factor is the square root of the expected value of that. Okay, so I have the square root of the expected value of the max over k of yk squared. Right, but the spectral norm of a matrix squared is the same thing as the square of the spectral norm. So this quantity is exactly L. Right, because there's the square root up here. So we get exactly that this is smaller or equal than, right, square root of CD sigma plus CD, square root of CD, times another square root of CD, plus CD L. Okay, and this finishes the proof of something that now looks a lot like an expected value of the spectral norm version of Bernstein's inequalities. Okay. And now there's a few questions, right? So one in particular is how well, okay, the main question is how do we prove this master theorem, right? Everything seemed to come out of this. How do we actually prove it, right? So this we'll do next class. But what I'll show you now is how to deal with non-symmetric matrices. Right? So matrices that are not symmetric, they're actually very easy to deal with once you have inequalities for symmetric matrices. Right, so I'll just very briefly show you what the trick is, and then next lecture we'll see the proof of the master theorem. Okay, so for non-symmetric matrices, let's say we have matrices S1 through Sn, and they're not symmetric, right? So they're not the same as a transpose. Then the way to deal with this is to just reduce the symmetric case by taking yi to be the matrix 0, Si transpose 0. Okay. So if you do this, then essentially the spectral norm, you can describe the spectral norms of these matrices, and moreover, when you look at the spectral norms of yi squares, then what will show, right? What shows here is just the spectral, is just the maximum. Okay, I can write this a bit better, right? So you have the spectral norm of Si transpose, and Si transpose, Si here, 0, 0, right? This is the matrix that arises. And so this is just exactly the maximum between the spectral norms of Si transpose, and Si transpose Si. And so if we use the inequalities on this new matrix, all the stuff that shows up are norms of things like our matrix times our matrix transpose, or our matrix transpose times our matrix. And essentially with this, you can, from the symmetric matrix case, using this reduction, you can prove all sorts of things for the non-symmetric matrices, essentially because of this equality. You just write down things in this way, and you see what each of the terms starts being on both sides of the theorem when applied to the symmetric matrix, and you get matrix concentration results for non-symmetric matrices. Okay? And so next lecture, what we'll see is the proof of this master theorem.